Welcome to the course on atomic structure and chemical bonding. My name is Mangala Sundar and I am a professor of chemistry in the Department of Chemistry in Indian Institute of Technology, Madras. Okay. My email IDs are given to you here. Now, in this lecture, we shall look into the first few lessons of the mathematics of quantum mechanics, and in doing so, we shall introduce the concept of linear vector spaces. The introduction to this is through vectors, but then vectors represented formally using matrices. As you know through the lectures in the last few, that the quantum mechanics proposed by Schrodinger started with the differential equation model, and we will be solving a few of the differential equations further in addition to what was already done. But the other form of quantum mechanics, this was done by the use of matrix mechanics, and that was proposed by Werner Heisenberg, Max Born and Pascal Jordan. Well, Werner Heisenberg, Max Born and so in this lecture, of course, I would give you an elementary introduction. I am not going to give you proofs and the mathematical definitions until the end of this lecture. We will start with some definitions and become comfortable using the column vectors and row vectors and matrices representing important quantities in quantum mechanics, the measurement quantities represented as operators using matrices. So, we shall do all those things, and towards the end of the lecture I shall give you a formal introduction to the mathematics in the sense of the definition using the axiomatic method of the linear vector spaces. But this whole lecture is still hands on, in the sense you should be able to do things as and be operational in the use of matrices. Please understand the Schrodinger equation, which is written as H psi is equal to E psi for this course, that is a time independent Hamiltonian with a wave function which of course is dependent on time, but its position dependence is what is more important to us. This equation is actually a matrix equation if you represent the Hamiltonian, which is an operator in the form of a matrix, and then you will see that the function psi is known as the eigenfunction, and the quantity E, which is a constant and which has the dimensions of energy, the total energy, is known as the eigenvalue. Therefore, whatever we do today and in the next few lectures will be very important in understanding the solutions of the Schrodinger equation using matrix methods. And today, practical calculations involving large scale programming and computational chemistry programs used in biology, used in medicine, used in material science, used in physics and chemistry, all use matrix eigenvalue problems as solutions. Therefore, this lecture is fundamentally important for us to understand the basics. Okay. What are the lecture objectives? To introduce the vector space, a special notation which has been used by Paul Dirac, Adrien Maurice Dirac, known as the bracket notation. To represent vectors using matrices, basically column and row vectors understand scalar products and norms of vectors, all using matrices. The sequence to this lecture will then represent the operators using matrices and will also give you a representation of the operators using what are known as the basis operator matrices and so on. Here in this lecture we will see the vectors being represented by row vectors and column vectors. Okay. In the beginning was Professor von Neumann, who published a very famous book known as the Mathematical Foundations of Quantum Mechanics. The mathematics in this course and in many other advanced courses in quantum mechanics have all built on the fundamentals and the foundational methods which were first proposed by Professor von Neumann. Okay. Now let us start with very simple vectors in 2 dimensions. All of you know that if you write any vector A in 2 dimensions, you normally represent this vector by some arrow, and the arrow tells you the direction in which the vector is pointing to, and the length of the arrow giving you the magnitude of the vector. Now one further step is to associate a coordinate system. In 2 dimensions it is a planar coordinate system in which the 2 coordinates x and y are orthogonal to each other, and if we represent the vector in the coordinate system, then we write this vector in terms of its components, namely the x component and the y component. Okay. So this is the unit vector in the x and y direction, and therefore you write the vector A in terms of the component in the unit direction A1x and the component in the unit direction y, so that you know that when you have to add this to get this vector, essentially you are adding A times x, which is the unit vector, and A2 times y, which is the vector in the y direction. So this is the point, and in a similar way if you write another vector B, it has a different component B1x plus B2y and so on. Okay. What do we mean by that? We mean by that the vector x dotted with x is unity, so scalar 1. The vector y dotted with y, the unit vector, is 1, and the scalar product between the 2 vectors x and y, if you recall the dimensions, the scalar product definition, it is the magnitude of x and magnitude of y multiplied by the cosine theta, where theta is the angle between x and y, and you know that theta is 90 degrees, therefore this is 0. Okay. So this is meant as the orthogonal and normalization representation of the unit vectors. Therefore when you write the vector A as A1 of x plus A2 of y, you know that the component A1 is nothing but the projection of the vector A onto the x axis, and that you know immediately it gives you A1 x dotted with x plus A2 x dotted with y, which is 0, and therefore, and this is 1, therefore you have A1. So you know that when you say component A1 and A2, it is a projection of the vector in that particular coordinate system. Projection of A onto the x axis, and likewise for x axis onto the x axis, and likewise for the component A2, it is the projection of A onto the y axis, which will give you A2 times y dotted with y, and that gives you A2. Therefore, these are projections, and the word projection is important also in a later context, therefore keep this in mind. Now, when we say that a vector A has a magnitude the vector A's magnitude is actually calculated as the magnitude of A dot A, the magnitude, and it is a square root. Okay. A dot A gives you the square of the vector A, and therefore the magnitude of the vector A is the square root of the A square, and that is also very easy to write down because you write this as A1 x plus A2 y dotted with A1 x plus A2 y, and it is a square root of it, and therefore that gives you A1 square plus A2 square and gives you the square root. Okay. Therefore, a unit vector in the direction of A is A divided by the magnitude of A. And so what you will have is therefore A1 by square root of A1 square plus A2 square on x plus A2 divided by square root of A1 square plus A2 square on y. So, this is what is called the unit vector in the direction of A. Unit vector in the direction of x is of course x hat and likewise y hat. Now, all of this is very familiar to you. Now, what is the matrix representation for all these things? In 2 dimensions, one represents the unit vector x by a column vector 1 0. It is a 2 by 1 column, that is it is a matrix with 2 rows and 1 column. That is what is the 2 by 1 mean. The unit vector y is represented as 0 1, and in matrix the scalar product between these vectors, if you want to write x dotted x, then the scalar product is actually x of t, the transpose of this unit this column multiplying the vector itself. So, the transpose of 1 0 is the transpose which is a row vector. This is a column vector, and the row vector multiplied by the column vector 1 0 gives you 1. Likewise, when you write y dot y in the matrix notation, it is the transpose of the column y representing the vector y multiplying the vector y itself, which is 0 1 multiplying 0 1 giving you 1. And in this notation it is also very clear when you write x dot y or y dot x, you know both of which are 0. Essentially what it means is the left hand vector is written as the transpose x t dotted y or as y t dotted x, and you can see right away that if you do this, x t is 1 0 and y is 0 1 which is 0, and likewise y t is 0 1 multiplying 1 0, and that is also 0. So, this is the translation of the idea of vectors in simple physical dimension in a geometric space into a linear vector space involving abstract quantities such as the matrices, column vectors and row vectors and so on. So, this translation is important, this representation is important in understanding how to carry on this process for vectors in general in n dimension, and then the scalar products of them, then manipulating those vectors with the solutions of the Schrodinger equation and all those things, etc. So, now given that if we write an arbitrary vector A, then you know we have written this earlier as A1 of x and A2 of y, and that obviously now written in terms of columns it is A1 times 1 0 plus A2 times 0 1, and doing the matrix addition you see that this is nothing but the column A1 A2, and therefore when you write the scalar product of A with itself, what it means is it is A t dotted with A, and so what you have is A1 A2 A1 A2, and you can see right away that this gives you a1 square plus a2 square. Therefore, what is a unit vector A in terms of matrices? It is the vector divided by its magnitude. You can see immediately the column is written as a1 by square root of a1 square plus a2 square, and the other is a2 by square root of a1 square plus a2 square. Okay. So, what is a scalar product between two vectors A and B? Again, the left hand vector is to be written as a transpose, which is a row vector, and the right hand vector remains as is. And so, you can see that this is a1, a2 and b1, b2, which gives you a1 b1 plus a2 b2. Now, is a dot b the same as b dot a? It appears so, because if you write bt dotted a, the vectors, then you can see that this is nothing other than b1 b2 multiplying a1 a2, and so you have b1 a1 plus b2 a2, which is equal to a1 b1 plus a2 b2 as long as a and b are numbers. A's and b's are numbers. This is important. We know that matrices in general do not commute when we take the product of two matrices A B, and then we compute the matrix product B A. It is not necessary that A B will give you B A. In fact, in general it will not give you that. Therefore, the matrices, the order in which you multiply the matrices are important, but if you are dealing with numbers, we do not have an issue. Okay. So, this is all elementary ideas. So, this is how we represent to the vectors, and this is how we represent to the scalar products in 2 dimensions. Now, how do we extend this to 3 dimensions? It is again very simple. You recall that an arbitrary vector A in 3 dimensions, if you have to represent it geometrically, you remember now there are 3 coordinate system, 3 basic coordinates, namely the x coordinate, and there is a unit vector along the x direction, there is a unit vector along the y coordinate known as the y unit vector, and there is a unit vector along the z coordinate, which is called the z. So, if I have to write this in some colors, maybe you can see that this is the unit vector z, and this is the unit vector x, and this is the unit vector y. And therefore, any arbitrary vector, if you do that, any arbitrary vector is basically, if you project that vector onto the xy plane, and suppose the projection looks like that, then you see that it is nothing but the projection of xy onto this plane plus the vector along the z axis. Therefore, A can be written as 3 components, a1 times x plus a2 times y plus a3 times z. Therefore, now you have in 3 dimensions 3 independent components, and these are nothing other than the projection of the vector A onto the respective axis in the unit the unit vectors in the direction of the axis. So, a1 is that, a2 is y dotted a, and a3 is z dotted a. Okay. So, this is something you are familiar with. Therefore, how do we represent this in terms of matrices? Very simple. You write this in terms of a matrix with a 3 row and 1 column, with the first row being 1, second and third rows being 0, and likewise for y 0 1 0, and for z you have 0 0 1. This is orthogonal coordinate system, meaning that the 3 coordinates or the 3 directions are mutually perpendicular to each other. Therefore, again it is possible for us to imagine that the unit vectors along these independent 3 mutually perpendicular directions will be orthogonal to each other pairwise. So, x dot y is 0, x dot z is 0, y dot z is 0, and likewise the other way around, y dot x is 0, and so on. Okay. And x dot x is 1, y dot y is 1, z dot z is 1. All these things are now replicated by these columns. For example, if you write x dot x is nothing other than the transpose of the matrix X with itself, and therefore you have 1 0 0 multiplying 1 0 0, and that is the number 1, scalar 1. And likewise you can show this to be y t dot y as well as z t dot z. Okay. And in the same way you have x dotted with y is 0 and y dotted with z is 0 and x dotted with z is also 0. So, again this is an orthonormal system. So, immediately you can see that any vector arbitrary which is written as a1 times x which is 1 0 0 plus a2 times y which is 0 1 0 plus a3 times z which is 0 0 1 is obviously the column vector a1 a2 a3, and therefore the scalar product between two vectors a and b if you have to write, and if b is the column vector given as b1 b2 b3 as the three components of the vector b in this in these directions, then the scalar product is a t dotted with b, and that gives you a1 a2 a3 the row multiplying the column b1 b2 b3, and the answer is a1 b1 plus a2 b2 plus a3 b3. And in a similar way the unit vectors of A are also very simple, that the magnitude of A is now the sum of the 3 squares a1 square plus a2 square plus a3 square root. Therefore, the vector A is obviously a1 divided by the magnitude, that is a unit vector in the direction of a1 divided by this magnitude, a2 divided by this magnitude, a3 divided by this magnitude. So, unit vector A if you write so that is the vector unit vector with a magnitude 1 in the direction of A. Okay. Now, we have been careful enough to write x t dot x. What about x x t? What about y y t or z z t in 3 dimensions or in 2 dimensions this, if you just do the other way around. Now, that is going to give you not a number, it is going to give you a matrix, and such things will become known as operators, and they will be fundamental in representing the quantum mechanical measurement quantities known as the operators, and therefore in the next part of this lecture or the next lecture we will continue with the definition of the operators. I hope this was clear enough for you to understand the connection between a simple vector representation in geometry and an algebraic representation of the vector using matrices, using columns and rows and taking the product. We will continue this in the next lecture to represent the operators. Until then, thank you very much.